All right, I'm going to give you your problem like I said I was going to. I'll write it on the board. Yep. Please. This nice and loud for me. Let's talk about that. Thank you for pointing that out. What a good question. In fact, go ahead. You can ask the question. Yeah, good question, and shame on me for not addressing that. An excellent question. So if we're asked, does gravity itself as a force generate torque? The quick answer is no, zero torque. And I'll show you why. So if this is that's really terrible, ugly, poorly done, poor effort. If this is the thing that's rolling down, since the center, remember that gravity, though, if you were dropping a block, we say gravity's pulling the whole thing down. But a thing is just a collection of many things, right? You are a collection of all the atoms in your body. So you could technically think that, this block that we would not usually think of this way is a collection of all these little segments, and each little segment has some weight and it's being pulled down, and this one's being pulled down with the same. And since they're all equal chunks, and they would all have the same vectors pointing down, and then you'd have to add up all of those vectors to say that the total weight is, a giant vector pointing down because of the sum of all those little ones. And then you said, well, what about the location? Conceptually, magnitude, the total downward force, is the sum of all of the little downward pulls on each segment added up, similar to rotational inertia, but nobody teaches us this way. So in magnitude, that makes sense. Then you'd say, but what about the location? These are all in different locations. So at what point, when we're referencing the whole object, where do we say that gravity is pulling down? You can't say it's at 20 different points because it's all 20 different objects. And I actually just made those 20. I could have made those far thinner and say it's 2,000 different little boxes. So there's 2,000 different points, and you can make them even thinner. It's 200,000. Then you up against a wall, realizing there's a problem in terms of the location. So what do we say? We say the center of mass, because that's the average location. There are some that are below, there are some that are above, so the average falls along the middle. And when you go this way, there's some to the left and there's some to the right, so the average falls along that. So the average location is actually in the middle. So that's the concept of center of mass. It works beautifully for a lot of physics stuff. When we come over to this, it will be the same idea. Technically, if the rotational axis is here, and you said that there was a little chunk out here, this little concept of little segments, a little piece of mass there being pulled down, then technically, since R goes this way and this would be its little weight, technically that gets some torque, right? However, what about the guy that's over here on this side? He gets some torque too, right? mg. And this is his R. What would those two torques add up to? 0. They'll cancel. The torque that's on the right side is trying to get this thing to rotate this way. The torque for this little black guy on the left is trying to get it to rotate this way. Since they have the same R and the same weight, since it's the same cube, there actually would be a cancellation effect. And you could technically say that for all parts. You could say that should be technically true for one up here, should cancel with one over here. One over here should cancel with one over here. And for that conceptual reason, you could say there's no net torque from gravity, because wherever you see one section on one side getting torqued, there's a section on the other side symmetrically getting a torque in the opposite direction. They cancel. That actually makes sense. The other way of thinking of it is that if you use the concept of center of mass, which I was doing on the right over here with the big block, if the center of mass, where is the center of mass? This is the center of mass. COM is usually short for center of mass. Where is the axis of rotation? That is the axis of rotation. They're in the same spot. To get torque, like for this guy that was over here, there has to be a force some distance r from the center of mass, from the axis of rotation, r. So you go from this axis of rotation out to wherever the object is applying force, and that's, again, the r you use for torque. So if we're thinking, well, if the object's center of mass is in the center, like I said over here, on the back over here, we never draw it like this on the right. Nobody even talks about it. I don't know why. It's interesting. I don't know. We pick and choose what we're going to talk about, I guess. What do we usually do instead of drawing it like I did? We say, this is where we draw, and we just say mg. M representing all of those masses added up. And this is the center of mass. So technically, when we come back over to this spot on the left, if the center of mass is, again, right in the center, right here, and that is also the axis of rotation, and we say, okay, the center of mass is where it has the whole thing's weight. The whole thing's weight pulls down from its center of mass, collectively. But what's R? What distance is that from the axis of rotation? Gravity effectively is pulling down on the center of mass in an average way. But again, there's no R. It has no, it's pulling down on the center of mass. The axis of rotation is also in the center. What's the distance from where it's applied, which is in the center of it, to the axis of rotation? There's zero distance. They're in the same spot. And therefore, you'd say that's just another way of looking at it. This value is zero. There's no distance between the gravity force acting at the center of mass and the axis of rotation, so it gets no torque. So those are two different ways of thinking of that. So know that when you're referencing these rolling problems and they're referencing torque, they're always only referencing the frictional force, since the frictional force does in fact act right at the bottom here. If it's if it's a sphere, then it's just a point. It's one point of contact, right? A ball, a sphere on a flat surface. Like if I painted this ball and then just pushed it against the floor and lifted it up, I'd see a dot, right? So that means that's the point of contact. That means all of the frictional force is being applied to that one tiny spot. If I decided to grab a cylinder like this one and paint this and then hold it in the way that I would usually roll it down a ramp, paint it wet paint, keep it wet, press it against the floor and lift up, am I going to see a dot? It wouldn't be a dot, right? It would be a line, actually. You'd actually get a line out of it. It'd be one line that extends. So all of the frictional force is happening along that one line. Again, there's a little here, a little bit here, a little bit here, a little bit here. Do we ever talk about that? No. We just always talk about the sum, the sum of all of those areas that are experiencing friction. They're all in the same direction. Vectors add, that's vector addition. And so usually we would just write, one vector pointing this way and say the frictional force. It is static because it's not sliding. Sliding means this thing is literally just sliding, like it's not rolling, it's just sliding down the ramp, and nothing does that. Nothing does that, so it's not a sliding friction thing, it's a static friction thing. If I put a stamp on this, if I took this, it's like tires for cars too, right? If I put a wet stamp on it and then had a nice flat piece of paper, and I lay it down, I'm not painting it like I talked about before, just putting a stamp, and I hold it on the top, and I take my stamp maker and I press it down and make a nice wet image of something, nice wet stamp on the top. I lay it on the paper, and then I push with my hand like this, and I roll it. What would the image look like after that top stamp finally rolls around and presses against the paper and then it comes off? Would it be smeared or would it be nice and clean? Anybody have a guess on that? For you to go like that with a wet thing, it would be a perfect press. It's a perfect pressing. You only get a smeared effect if it's sliding. It's not sliding. It's pressing. And so during the time that it's in contact with the ground, that one area that's touching the ground it's not sliding across the ground in that moment. It's just pressing itself into it in a static way. And then a moment later, they're not even touching. So during the time of contact, it's a static effect. There's still an interaction between them, but it's not a sliding effect. So just remember, it's a static friction that we've been talking about. And this is the only torque that's important. It's not the only torque that's important. It is the only torque that actually causes it to roll. And again, in a direction that would be the direction that you would expect. This thing would, roll down the ramp like that. All right, good question. I'm going to switch gears now and give you that problem to try, see how you do with it. All right, so we're going to try one that's similar to that problem. Again, the static problem. I promise you'll see something that looks just like this more than likely on the AP exam. The beam and the rope is a very famous problem that they pick usually to assess student understanding of torque. I'm also going to put, so I'll have to put some numbers obviously in here. So let's call this an 8-meter beam. And then we're going to place a block. This is what they would do to you at a distance of 2 meters. I mean, different numbers, but it wouldn't be just the beam and the rope. The standard AP problem is a beam with something standing on it. It's either a person or it's a block, or it's, they get cute with it. They put an animal on it or whatever they decide to do. But they add some additional thing to it. They have the beam, they have the rope. They would give you, they'd have to, the mass of the beam. I'm going to make just random number, doesn't really matter, 50 kilograms. The mass of the block, which again doesn't really matter, but I'll just make it as 5 kilograms, let's just say. We would always say that the rope has negligible mass. Because otherwise we'd have to consider that part too. They don't want to overcomplicate it because it's already complicated. Then they'd give you the angle. I guess this looks like it's 30 degrees based on how I've drawn it. They're not going to give you 22 or 73. It's usually 30, 45, or 60. And then my first question to you is, write down or generate, or maybe not write down, generate a formula that reflects that the net torque is equal to 0. So you don't have to solve it. Do not solve it for any variable. More than likely, that's probably what would come into the play, other than some concept questions. But if you're actually doing some mathy stuff, them asking you to go a deep calculation, probably not enough time for it. But they would probably say, especially if this was a free response question, create a formula that reflects the idea that the net torque is 0, because this is a static equilibrium thing. I will remind you that torque is created from gravity in this case. The weight of the beam creates torque. The weight of the block creates torque. The weight of the rope, nope, we decided to not overcomplicate it. We're saying it's a very thin, lightweight rope. That said, you have to use the center of mass. You have to use the center of mass idea, where this is the force of gravity on the beam. Similarly, center of mass of the block. This is the force of gravity on the block. And when you're doing your torque stuff, it's the distance from the pivot point. This is the pivot point. Think of it as the axis of rotation. So R goes from there out to the center of mass. Right? So R for the block is shown, and you'd have to figure out what R for the beam is. And also remember that those two torques are on the same team. So in an equation, they should be on the same side of the equation. Both the weight of the block and the weight of the beam are both trying to get this beam to rotate in the counterclockwise direction. It's not, because there's some counter torque from the rope, which is pulling in a way that would get the beam to rotate in a, I said that backwards. The weight of the beam and the weight of the block are trying to make this beam rotate in the clockwise direction. I think I said counterclockwise. They're trying to make this thing fall in the way that you would usually visually see it. So gravity's trying to make it rotate the clockwise way. The rope is trying to make it rotate more up and to the left, the beam, the counterclockwise way. And that rope is on its own team by itself. There's nobody helping the rope. It's a rope against two gravities, right? Just remember that. It's an easy idea, because if you're showing that they all add up to 0, the total from one team has to equal the total from the other team, right? Yeah. Little louder. No numbers for this, just representing these things as symbols. Yep. They wouldn't actually ask you to put numbers in, probably not. So we're just trying to create something that is referencing that the net torque is equal to 0 using symbols. That's probably all they would do. Or they would show this answer of this to you as a multiple choice, A, B, C, and D, and say which is the correct equation that reflects this idea. So give it a go. When you get to the torque that's being created by the rope, you're going to have to do some geometry stuff, right? You got to think about components for the torque that's, again, occurring due to the rope connecting with the end of the beam. You got to think angle, you got to think sine, is it cosine? You got to think tension force from the rope. That whole bag of stuff comes in for that part of your modeling. Just giving you little hints, that's all. Total torque from one team equals the total torque from the other team, if it's in static equilibrium. If that's not true and one team gets more torque, it's not in static equilibrium. It rotates in the direction of the stronger team. I am going to just change the screen for a second. I haven't taken attendance yet. One, two, three, four, five, six, seven, eight. Oh, I was supposed to send this down. Shoot. Shoot. I did not get. All right, I'm gonna be right back. I have to run this down to the office. Don't go anywhere. So I'm going to add another part to that. You may not be ready for it, but you might. So if you could just listen to what I'm adding. Another part which is important to be able to do, question 2, is going to be about the rotational inertia. So question 2, I guess I'll put up here. What is, I'll just put I, which is the rotational inertia of the beam plus the mass. So remember that when you're dealing with rotational inertia, each thing in the system can provide some rotational inertia to the total that the system has.
Mr. Kurzak, you're not presenting your screen to us anymore.
Oh, sorry, I forgot. Thank you.
You're welcome.
Present. There. Okay. So I want you just to stop for a second. Just listen to what I'm saying, if you could. The second question is, what is the total moment of inertia, rotational inertia, for the beam? Because it can rotate, right? It's not. That doesn't mean it can't. It just means it's not. It could rotate again if the rope breaks. If the rope snaps, then this thing would rotate. The left side, where it's in contact with the wall, would have some friction that would kind of catch it, and this thing would rotate in the downward direction. And it would have some rotational inertia, because all things have rotational inertia as long as they have something trying to torque, provide torque to it, which gravity is for the block and the beam, and there's some distance from some axis of rotation, then gravity will find some resistance and difficulty in making them rotate. And so again, the total rotational inertia of the beam plus the block is equal to the beam's rotational inertia about that axis of rotation plus the block's rotational inertia about that same axis. You just add them together. You treat the block as a point mass. Remember that for a point mass, the rotational inertia is just mr squared. R would be, again, from the wall to the block. For a beam, I don't know. To be honest, I don't remember it. You can look it up on your computers if you want. I'll just tell it to you, save you time. They usually would give it because, again, you do not have to memorize any of the rotational inertia formulas from that chart I showed you the other day. 100% tell you you do not have to. The concepts you have to understand. If it's useful, needed rather, in a problem, they'll just give you the formula right in the problem. They'll say, rotational inertia of a disk is 1/2 mr squared, whatever it is. So I'm going to search for rotational inertia of a rod. So we usually call the beam a rod. Is that a good spot for it? We need to find that fractional coefficient. I don't remember it. Here it says 1/3 ml squared. And I believe this website. 1/3. So I'm going to tell you that the rotational inertia for the beam, it's always m times either r squared or l squared. So for the beam, back to my, where am I? Where's my, sorry. So for the beam, L is just the full length. L is in the ml squared. L references just the full length of the beam. So the rotational inertia of a beam, assuming that it can rotate along one end, not if the axis of the rotation goes through the middle, that's different. If the rotational axis is on the end, then the formula for any beam or rod is 1/3 ml squared. You can jot that down if you want. If they asked you, what is the total rotational inertia of the system? Just add them together. It's the rotational inertia of the beam plus the rotational inertia of the block. Just remember that the block is considered a point mass. That's it. You can add that to what you're doing for part 2. A little louder? Yep. As an expression, as a algebraic expression. Yep. Oh, I should point that out. I don't want you making calculations. Yeah. We would usually call it just the total inertia, but yeah, that's right what you said. Just pointing out, I'm not looking for you to make any calculations. This is just algebraic expression. For the total rotational inertia of the box beam system, that's what they would say. That's the way they would word it. And when I said plus mass, I meant plus the box, right? Beam plus box. I'm just trying to squeeze in as many ideas as I can into this problem, because after we leave this problem, I'm not ever going to return back to it. All right, just a few more minutes, and then I'm going to switch gears a little bit. All right, so I'm going to return to this. If I could now. So for this problem, so yeah, even though I put numbers down, I guess they weren't necessary because I don't think it's useful necessarily right now for you to make it a long calculation. That said, if we were looking at the torque for the box, then this is the R for the box. I'm not sure why my pen's doing that. And then this would be the mass of the box times G. So I know that the torque created by the weight of the box would be R times the mass of the box times G. I put the mg in parentheses because that represents the weight of the box. I would say the same thing for the beam. Do the same thing for the beam. And say if I'm just kind of looking separately at the beam right now, you got a lot going on a page, I'd recommend just looking at each part slowly and individually, then you combine everything in the end. So if I'm looking at the beam has a center. Yeah, the beam has, has a full length like this, but again, we're looking at the center of mass. Technically, this, again, little chunk gets a little bit of torque. If I was showing torque, this vector as a torque, this would be a little more torque. This chunk here would get a little more torque. This chunk here would get a little more torque. Not because each chunk along that line has more weight, but it's getting more leverage. It has a larger distance R. So the torque for the parts of the beam that are to the left get less torque than parts all the way to the right, which is why if a man was walking on this beam, his own weight would cause a lot more torque when he gets to the edge of the beam because his position is now far away on the tip of the beam, and therefore gravity is pulling down with still his weight. That doesn't change as he walks back and forth, but his R distance is changing as he walks back and forth. All the way out on the edge of the beam, he would create the greatest torque in the direction that would cause this beam to rotate clockwise. And the only thing to combat that would be the tension in the rope. So the rope would be the tightest if he was all the way out on the edge on the right, because the tighter tension in the rope provides more counter torque in the other direction to compensate and counter the extra torque of the man when he walks closer to the right. And then again, so that's just like an idea, the profile, that torque always gets greater for things as they move outward. So even for the beam. But again, we don't add them all up and do all that stuff. You get the same result if you were to take all the time to do that, get the exact same result as if you just treat the center of mass as here, and R goes from here to here. And this is now just the mass of the beam times G, right? So we could say the same thing for the beam. The torque created by the beam will be R times the mass of the beam times G. And then and those are on the same team. So if I want to call them both plus, then they're both plus. If I want to make them minus, they're both minus. They're on the same team. Anybody on the same team has to have the same sign. Only people on opposite teams have opposite signs because they're against each other. Against, plus and minus are against. So now if I'm doing the same thing for the rope, which I think is the more challenging part of this, that involves a little more geometry. Now we'd have to look at the idea again that the rope has some tension. As a vector, we're pointing it in this direction. That's the tension in the rope. And it has components. And it will be as strong as it has to be, essentially, to make it not fall, right? Like, that's a variable thing. If things were moving around on this beam, that tension, again, would decrease and increase and decrease and increase as much as it needed to make it so that the net is zero. Hopefully, you don't go so far that the total torque in the downward direction requires more torque from the rope than it can possibly do, and then the rope snaps, and then you're in trouble. But if it's a super strong rope, it'll adjust itself however it needs to with its tension to prevent the whole system from falling. That said, this is FT. This would be FT well, yeah, weird to write FT perpendicular because T and perpendicular, same symbol, but flipped. So that's FT perpendicular because R again goes from the pivot all the way out to where the rope is attached. That's the whole length of the beam. And so we'd have to think, all right, that's the piece that we want. That's the part that's getting torque. The part that's F perpendicular that I just drew in right here. So if we think of this as a, should I, am I able to use 30 degrees as that angle? If I want to use this angle here, then that would actually have to be 60 degrees. And this is where I tell you, you have to be careful here when you get to these triangles. Don't assume it's going to be sine or it's going to be cosine. Look at it. If I'm going to use the 30-degree angle or the 60-degree angle, it's up to you. But just know that that's a choice that you'd have to make. Usually torque goes with sine. When you look at a textbook, the torque formula has as F R sine theta in it. If you're going to do that, then that would have to be this angle right here. You'd have to use this one because sine goes with opposite. And the opposite that it's pointing to is F perpendicular. If you decided to do that, yeah, you can use the 30 degrees because those are the same, opposite interior angles. But if you chose to use the 60, then you would end up having to use the cosine, right? If you decided to use the 60-degree angle. So if I'm using, this is still a 30-degree angle. It's just like a square. Again, I know that's kind of messy, but if this original one here is 30 degrees, then this one here is also 30 degrees. And then again, the opposite to that, because that's where I drew my F perpendicular right here. F perpendicular is that one right there. So I can now say that that perpendicular force, F perpendicular, is equal to the magnitude of the tension, which is the total full strength, tension, tightness of the rope, times the sine of 30 degrees. Right? Because it's opposite to the 30 degree. Opposite goes with sine. And then I know the torque that force creates has to be that force times R, because that's what torque is. It's force perpendicular times R. R, on the other hand, remember, is the distance from the pivot all the way out to wherever it's being applied. And if the rope is tied there, then it's being applied there. Instead of putting R, a physics AP exam would end up putting L there. Just be aware of that because R is L. L is representing the length of the beam. R goes from the wall out to the edge of the beam. Well, that's R, it's L. They don't put R, they put L. Just be aware. So as soon as I throw an L in here like this becomes torque. This becomes my last piece. Now I can say the torque due to the rope so this is an expression for the torque due to the rope. They're on team 1. These are the torques due to the gravity. This is team 2. Like team 1, this is team 2. And so I know that the total torque due to team 1 has to be equal to the total torque due to team 2. Because that's why they cancel and the thing doesn't move. So all I have to do is represent that conceptual idea in a formula. The torque due to the box plus the torque due to the beam. Their team, what I called team 2, I guess, has to be equal to the torque due to the beam, which is, I guess, what I called team 1. So then to express that, I'd have to put all those expressions in. I'd have to put in R right here, R times the mass of the box times G, because that's coming from right here. Then I'd have to use this one for the beam, R, so it's plus, that's a plus sign, plus R. Oh, and those R's are different, so I should be careful there, sorry. Mass of the box, I don't know, maybe I'll call that R box, because remember, the R for the box only goes from here to here, where R for the beam goes from the wall to the center of the beam. So I would have to be careful of that. Those are not the same R. R, I'd have to label it as R beam times the mass of the beam times G. That's this here. is be equal to now the torque due to the, I didn't mean to write beam here, sorry. I meant to write rope there. This has to be equal to the torque created by the rope. So which I have that right here. Magnitude of Ft sine theta, or sine, yeah, I'll just leave it sine theta, times L. Because they probably would have just had theta in here. They probably wouldn't even put the number. They just say theta. And so this whole thing is reflecting the idea that all of the torques add up to zero. Because that's the concept of static. Anything that's an equilibrium, total on one side has to equal the total on the other. If it was me in a box, like boxes on the table, and I'm pushing it with some force to the right, and my friend is pushing it with the same amount of force to the left, and it's in static equilibrium. If they said, write a formula that expresses that, well, the force from Mr. Kurtizak to the right equals the force of Jimmy to the left. That's it. They must be equal because they're canceling, it's not moving. If you actually had to solve for the tension, you could. I don't imagine they would make you go that deep, but you could actually solve that. If they said, and the last part is, here's all the numbers, good luck, solve for the tension. That would be a doozy, but they could, just FYI. They would give you L, they would give you the theta, they'd give you all the masses, G you know, they'd give you all of the R's, G you know, mass you know, R's you know, they'd give you everything. They'd give you all the information and say, what is the tension? And there it is. You'd plug all of that stuff in and then do algebra to solve for the tension. That's how you do it. Conceptually, remember, though, that the tension depends on the weight of the beam, depends on the weight of the box, depends on where the box is. If the box was out further to the right, the tension would increase. It would have to compensate for the extra torque that the box is getting if it's being shifted to the right because of the extra R, extra leverage distance. And the tension in the rope also depends on the angle of this rope, how they actually created it. If it was a much thinner angle, like I said in that lesson that I had you watch, if it was only 10 degrees, and like that rope actually came from here to like here, then it'd be much, much tighter. It has to be much, much tighter so that it can still produce enough torque to fight against the other two. Yep. Yep. No, they'll want you to write it like I did, unfortunately. I know what you mean, like f of x plus g of x or something like that. No, they'd actually, yeah. That's how they are in physics. They want to see the full stream. They want to see all of it. Usually because you might end up solving it and you like have it all, solving it for one particular variable, or reading proportionalities so that when they're all in symbols, you can say, oh, this is proportional to this, or that's usually why, I think. It's a good question, though. All right, I'm going to, it went a little longer than I wanted to, but I mean, I had to do that. I wanted to at least give you a chance to try something. I won't talk about that again. That does come up on the exam. We won't talk about that ever again. I'm now going to talk about the ramp. I don't know that I have enough time to actually work out the proof, but I will probably just do that on paper, PDF it, I'll post it for you. I will summarize that any object racing down a ramp with another object, and this problem comes up as a multiple choice question. They say a sphere, a hoop, it's always the sphere, the hoop, and the disc. Always. If it's in there, that's what it will be. I've seen it multiple, it's not every year, but it's very frequent. They say a sphere, a hoop, and a disc are raced down a ramp. What is the ranking of the race? You have to know that if it was a large hoop against a small hoop, it's a tie. If they're the same large hoop and small hoop that are the same mass, it's a tie. If it's a large hoop that's much heavier than a small hoop, it's a tie. Because if they have the same geometry, it's a tie, regardless of whether their radiuses are different or the masses are different. You guys proved that in the lab. And that's true for all of them. It's a giant sphere against a small sphere, it's a tie. If they're a giant sphere and small sphere have the same mass, it's a tie. If it's a giant sphere and a small sphere that have different masses, it's a tie. All geometries tie with the same geometries, period. You need to know that. The only thing that differs the race is when they're the different geometries, and that depends on this rotational inertia, which again, you don't have to memorize this stuff, but I do recommend you writing down at least what I'm telling you now. The order of this race, does anybody know who would win based on the homework? Did you try it? Who the winner is? Who should move down that ramp the fastest? Yeah. No, the rod, that's a good rod is not in it. So this is just top left, disc, middle, hoop versus sphere. Yep, sphere wins. All you have to do is look at the coefficients. Think of 1/2, like, well, the denominator on the sphere is 5, 2/5. So you can think of the one on the left as 5, well, 2.5 out of 5. I mean, you could put them all over 10 if you want. So you could say that the one on the right, 1/2 is like 5 over 10. The hoop is 10 over 10 because that's 1. And then this one on the right, 2 over 5, that'd be 4 over 10. So whoever has the largest coefficient, I mean, it helps to put them in lowest common denominator if you want to kind of get a sense of the order. Whichever one has the largest coefficient has the most inertia, which means it's harder to get it to rotate. That's not good for it. It means if its aim is to win, it's going to lose. It's harder to get the thing rotating. It slows its process down as it rolls. So comparatively, when we look at those, again, we end up with a 5. I guess I could. We have a, oh yeah. So when that's not full screen, it doesn't work. I finally discovered that. It's on, it does that. So 1/2, so it goes what? Disc, hoop, sphere, 1/2. So disc, hoop, sphere. So this one was just mr squared, which we could have thought as 10 over 10. This one was 2/5, I believe, right? 2/5 mr squared, which we could think of as 4/10 if you wanted to. Think of that as 4/10. And then what was the other one? I don't remember. This was the disc. Yep, 5 over 10. So the disc was like 1 over 10. I'm sorry, 1/2 mr squared. So you can think of that kind of as 5 over 10. So to me, it makes sense to just compare these numbers. Oops, sorry. This one, not 2/5. Just put them in all under over 10. Or if you say, yeah, I didn't need that, that's fine. I get it. But anyways, the largest number is this one. It's the hoop. 10 over 10 is certainly more than 5 over 10. 10 over 10 is certainly more than 4 over 10. So the hoop is the slowest. He loses. He loses the race. He places third. Who wins the race? Whatever one is the easiest to get rotating. Easiest to get rotating means a small inertia, a small amount of rotational inertia. 4/10 and 5/10 are close, but they're not equal. So 4/10 is the smallest amount of inertia, so he wins. Because of 4/10 is the least amount of inertia. And then number 2 is the disc, places second. So let's see if we can prove it. That's my goal in the last few minutes. I have them. I got it set up. And again, I will end up during my break doing that assignment, and I'll post it for you to look at. More exciting is actually seeing it. So we're going to erase any hoop, because again, the mass doesn't matter, the race doesn't matter. We're going to race the hoop against a sphere. I hope the difference is significant. Can you actually help me out with this? Oh, yeah. So you're going to have to hold that. I know I have 5 minutes. I think that's enough. Ooh. I think that's enough time. I do have to switch my camera. Camera is here and then here. So I think from other years when I did this, it's significant enough to see the difference. Can you actually come maybe over here and just point straight down it? Lift up, yeah, like that. So and now the harder thing of this to do is to get them to be released at the same moment. If one only wins by a few fractions of a second, well, then letting them go at the same moment becomes pretty critical. The most I can do is use my meter stick like I had done in another year. And again, will they actually roll on this thin little track? I don't know. We'll try. What would the prediction be for the winner? This should be the winner. Easily. It killed the hoop. I don't know if you saw that. By the time the ball was here, the hoop was like back here. We saw that on a slow motion camera. So the ball, the sphere, beats the hoop, which we know is supposed to happen. And then if we do the ball against the disc, this is a solid disc, by the way. This is seriously solid. The other one was a hoop. Pretty close. That one would have been hard for me to see without a camera. Closer than I'd like to see it, but let me try one more time, because it could have been my release. What do you think? It's close. It's hard to say. Yeah, I know. I think what I'm going to try to do is do that on a slow motion camera, and I can post it for you to watch. Wait 1 second, because I do think the sphere slightly wins, because the sphere's rotational inertia and the disc aren't that far off. However, there's still two left to race, right? Be the disc against the hoop. That was clearly a winner. The disc easily won that. When the disc was at the bottom right here, the hoop was still like 2 feet behind, which proves that that at least alone, I think, proves that the sphere is the highest, the hoop is the slowest, or the other one has to be in the middle. You can hand that to me. Thank you. All right, I think we're pretty much out of time. Again, I'm going to post the solutions to the homework, because that's something I think you should be able to review. I didn't get a chance to go over the rotational inertia. I'm going to have to start recording a lot of stuff, and I know that, because I have a week and a half to get through a fair amount of stuff. So I might even record my little lesson on rotational inertia, which I would have liked to do today, and put it in a puzzle. Just be aware. Probably be only I didn't mean to say rotational inertia. I meant to say rotational momentum, which I didn't get to do today, which should only be about a 30-minute lesson. So just keep an eye on that. I know I do see you guys. Today's Thursday, right? Yeah, I see you tomorrow. So if I do post something, it's not going to be, a whole slew of things, because I know I see you tomorrow. But I'm probably going to post one thing for you to watch tonight to make up for the fact that I didn't get to do everything I wanted to do. Other than that, I will, and again, I'll post the solutions to the homework that you guys submitted. Because you can prove mathematically the order of what we saw. And I'll post that for you. All right. Everybody home, hope you have a good day. I'll see you later. 1 second, let me just stop this.